In this video, we're going to be looking at nerve impulses and how nerves are conducted down an axon and relating it back to this graph. These are the learning intentions to go with this lesson, and hopefully by the end of this lesson you'll be able to comfortably use all of these key words in a short or an extended response. First of all, we're going to be looking at the word potential and what that means. The potential in relation to a nerve impulse is looking at charge. So when two opposite charges are separated by some sort of barrier, they have the potential to come back together. And when those two opposite charges come back together, energy will be released, and hence there is something called the energy potential, or commonly we call it the potential difference. And this can be measured in volts or millivolts. Because we're looking at neurons, we're going to be measuring this in millivolts. So what does membrane potential have to do with the nerve axon? Well, if we look at this image of a nerve axon membrane, inside the nerve axon, it is negative inside and positive on the outside. So if you remember, ions are charged particles in solution. We should note that there are a significant number of sodium and chloride ions outside of the nerve membrane, but there isn't very much inside. As a result of that, we have an overall positive charge outside the axon and an overall negative charge inside. And the reason for that is because inside the axon there are lots of potassium ions and other negatively charged ions and anions. The reason why we have this potential difference is because there are more positive charges outside than there are inside, which means that there is this potential difference, and therefore the resting membrane potential inside the membrane has been measured to be at minus negative 70 millivolts. Now that is a number that you need to remember. So this part in red here, talking about the resting membrane potential inside a neuron being negative 70 millivolts, that's something that we'll come back to. All right, so as we've said, the intracellular environment, so that's inside the axon, is more negative than the outside. So we're choosing our words carefully here. There are a lot of sodium ions outside rather than inside the axon. And conversely, there are more potassium ions inside the axon membrane than outside. So in this little animation, you can see that at the resting state here, there's more potassium inside than outside. What we tend to find with the axon membrane is that the potassium can easily get out of the membrane. So it's the way that the membrane is formed, it's a little bit leaky to potassium ions. To maintain this membrane potential, there are giant negatively charged particles inside the membrane, or anions, and this creates this polarizing effect. So even though we have a little bit of leakage of potassium ions going on, the overall effect is that we certainly have lots of potassium inside, but lots of negative charge inside, and sodium outside, and more positive outside. Here's just another diagram to illustrate that. So we're looking at the inside membrane, the intracellular environment being more negative, and the outside or extracellular environment being more positive. Therefore, we have this polarizing effect. Before we actually talk about how nerve conduction occurs, we need to do a bit more background here. So we're going to be looking at something called a voltage-gated ion channel. Now, these are some of the membranes found in the surface of the cell membrane. Sorry, some of the proteins found on the surface of the cell membrane, and these allow certain ions to pass inter or extracellularly. When this ion channel here is open, ions will diffuse, so that's passive movement from an area of high to low concentration down its concentration gradient. Now, these channel proteins are found in neurons, but there are other ones which are a little bit more specific, which we are going to be looking at. So there are voltage-gated ion channels which are specific to sodium or potassium ions. So that's ions that we have mentioned previously. These are specific gates, if you like, that will allow the passage of sodium and potassium in the nerve. So these protein channels can remain open or closed. The normal state for them is to remain in this closed position, therefore they don't allow anything through when at rest, hence why we get to maintain a resting potential of -70. When these channels do open, however, we'll talk about why that happens later, the permeability of their specific ion will increase, and therefore the flow of ions from one location to another will increase. Here we're just showing a simple cartoon for how this voltage-gated system works. So in the off position, when the gate is closed, no ions can travel through. When this channel is open, when this gate opens and this channel widens up, we start to have an influx of ions. Okay, so the ions have channels, and there is also something called the sodium-potassium pump. So just to remind you, active transport is the movement of particles against the concentration gradient. So that's to say we are moving from a low concentration to a high concentration. Within the axon membrane, these pumps will specifically work on sodium and potassium, and they will pump these ions against the concentration gradient. So what that means is that when there is lots of sodium outside of the cell and potassium inside the cell, it will work in a way to transport these ions against the concentration gradient. So we know that there's lots of potassium inside the cell, and this sodium-potassium pump will keep working to maintain that. So the overall effect is that we stay at this maintenance resting membrane potential of -70, because this sodium-potassium pump is actively going against the concentration. So again, with potassium, we can see there's only one particle out here, and there's lots inside, and yet we're still transporting it in. And on the opposite side of that, we've got two sodium particles here that are being actively transported out of the membrane. So just to summarize what we talked about so far, we know that the membrane potential is a difference in charge, and this charge is measured in millivolts. The resting membrane potential for the axon fiber is -70 millivolts, and this results because of this potential difference. So the inside of a resting neuron has large negatively charged particles called anions. Don't worry about the word anions if you're not a chemistry person. Just you need to know that they are large negatively charged particles. And there's lots of potassium ions inside the cell compared to outside. Outside of the cell, however, we have lots of sodium ions, thus making the outside or the extracellular environment more positive than the intracellular. We know that the potassium channels are a little bit leaky, so we start to get diffusion of potassium ions outside of the cell. However, that leakiness is corrected by the sodium-potassium pump. So this is where we have active transport transporting that potassium back into the cell and sodium out of it, thus maintaining our resting membrane potential. There's another type of protein found on the cell surface, and those are the voltage-gated ion channels, which we're going to go on to talk about. And when these voltage-gated ion channels remain open, then the sodium or potassium ions that they allow through will move down the concentration gradient by diffusion. So that's a passive form of transport. These channels are normally kept closed, however, and it's just the sodium-potassium pump working in the background. All right, so now we're going to be looking at the first part of our action potential or nerve transmission, and that is something called depolarization. So when we alter the permeability of sodium ions, so that means the gaps in the potassium channels and the sodium channels widen, their ions can start to move down their concentration gradients. So if the sodium channels start to get wider, sodium will be able to enter the cell, and this creates the nerve impulse. So sodium channels open, and because of diffusion, the sodium will move into the cell down the concentration gradient. Because lots of positively charged sodium ions are moving into the cell, it makes the internal environment less negative than it was before. What we have done here is we've changed the potential difference. So the charge between the inside and the outside of the cell has changed. It has gone from -70 and it's starting to climb all the way back up to 1 and or even 0. So that means it's becoming less negative. That's why we use that terminology. In order for the cell to do this, it's described as depolarization. So just as a summary in this cartoon here, you can see that the sodium channel has opened and there's more sodium outside than inside. So in depolarization, we are looking at simple diffusion. Sodium ion channels open and sodium diffuses from a high to low concentration gradient. Because we have more sodium moving in, this means that the internal environment is less negative than it was before. So for example, if it climbs up to -60, that's less negative than -70. Now you'll notice in this diagram, the potassium channel remains shut. So in depolarization, we are only focusing on sodium channels opening and sodium entering the nerve axon, and this is depolarization. So, okay, let's keep an eye on our two protein channels that we've talked about. The first one is the sodium-potassium pump. This is at rest. So the sodium-potassium pump is working in the background, but the sodium voltage-gated ion channels are closed. So this is at rest. In the case of depolarization, we can see that our sodium channel here has opened and the potassium one still remains closed. And what we have happening is neuron depolarization. Our sodium-potassium pump is still working away in the background, but it's losing the battle here because the sodium channels all open. Therefore, sodium starts to rush into the cell down its concentration gradient. All right, so this cartoon again is just showing that this series of depolarizations caused by diffusion, so these light green positive circles here are referring to sodium ions. They will diffuse into the membrane all the way along the length of that axon fiber. Now, because excuse me, because the sodium channels open and they start rushing in, it causes a wave of excitation happening here. So the inside of our axon is no longer negative, it has become depolarized. Okay, so in this picture here, we've got a simple illustration of how the sodium-potassium pump works. I've mentioned that before, but we're just going to add a little bit of extra information there. So what we need to know is that the sodium-potassium pump will transport 3 sodium ions outside and 2 potassium ions inside. So it's constantly doing this in this 3:2 ratio to try and maintain the membrane at rest. This doesn't always happen when we have depolarization, but that is what we want at rest. So here's a quick summary again of what we've just talked about. A nerve impulse is caused by a change in electrical charges inside and outside of the cell. So the first step in the firing of a neuron is known as depolarization. Now, depolarization is simply when the sodium channels open and sodium ions will rush into the cell by diffusion. So this is a passive movement of ions. In the background, the sodium-potassium pump is still working, but there's far more sodium coming into the cell than the pump can remove. So because the sodium-potassium pump is outnumbered, so to speak, the separation of charge is no longer there. So what that means is the inside of the cell will start to become positive, whereas before we maintained it as negative. This action of sodium moving into the cell is what starts a nerve impulse and is known again as depolarization. Here is just a little summary cartoon of what we've talked about. I would recommend that you pause the video here and write yourself a little summary of what happens from resting through to depolarization. Okay, so now we're going to look at this classic graph. We have got this action potential graph. We've got the membrane potential measured in millivolts on the y-axis and time on the x-axis. So far we have focused on the resting potential, which is here at negative 70 millivolts, and we've looked at depolarization. Depolarization is from negative 70 up to threshold value. Depending on your source, it could say negative 55 or negative 50 millivolts. Either of those two values is acceptable. And we see that we reach all the way up into the positive region. So this from negative 70 all the way up into the positive region, this is classed as depolarization. So there are other stages of the action potential. So I've talked to you about depolarization already. After that, we have repolarization, hyperpolarization, or the refractory period, and then a return back to resting potential. So we're going to be discussing how this action potential is carried out through each of these stages. So we've talked about the fact that the sodium channels are closed at rest when the resting membrane potential is negative 70 millivolts. We know that the potassium-sodium pump is working in the background. This uses ATP, so that suggests to us that it's an active transport pump. For every 3 sodiums that are transported, 2 potassiums are transported. So just a reminder, 3 sodium ions are transported out of the cell, whereas 2 potassium ions are transported back in. The reason why we have this going in the background, just as a reminder, is because the potassium channels can be a bit leaky. So at rest, we want to maintain this negative 70 millivolts and keep that polarization occurring. As an action potential is fired, we know that the sodium ions enter the membrane, causing depolarization. This energy change, where sodium ions start to rush into the cell, will stimulate even more sodium channels to open, thus having this massive influx of sodium into the cell, and it's causing that chain reaction or domino effect. This means that the cell becomes further depolarized, and as a result of that, there is a change in the potential difference. So we no longer have this clear separation between positive outside and negative inside. Because we have this sodium channel opening happening, the voltage-gated ion channels will also respond, and they will open also. So if we go back and look at this graph, at this point here, at the resting membrane potential, negative 70 millivolts, sodium channels are closed and the membrane is polarized. So there is a separation of charge, positive on the outside, negative on the inside. At this point here, where we start to see a change in the voltage of the membrane, there has been a stimulus. A stimulus is regarded as a change in the environment, so we're referring to it as an energy change in the environment, and this will stimulate sodium channels to open. Now you can see here there's a few failed attempts. Now this is because there wasn't enough of an energy change in order to reach this threshold level. Here we're showing it as negative 55 millivolts. Therefore, there was not an action potential that fired. So these are failed attempts. Okay, so a quick summary again. The initiation of an action potential occurs from a stimulus, which is detected by a receptor at a nerve ending. If there's enough energy to reach threshold, then there is a very rapid reversal of polarity of the membrane, which means that we don't have this positive on one side, negative on the other anymore. We are changing the membrane potential. As a result of this energy change and stimulus, the voltage-gated ion channels for sodium will start to open, and sodium will start to rush into the cell along its concentration gradient. This in turn causes the inside to become more positive than the outside of the membrane, and therefore we have depolarization. All of this starts at the axon hillock, which is the very starting point of the axon as it comes out of the cell body, and this will move along the length of the axon fiber. So here I'm just showing you, this is the axon hillock, and this was where action potentials start, and they will travel all the way down the axon fiber to the axon terminals. Okay, in this picture here, we are just showing what's happened as a result of depolarization. You should note that the little voltmeter here is now displaying 0 millivolts. We are no longer depolarized. This would be a good point to stop the video and write a couple of summary notes explaining what's happening, trying to use your key terminology. As before, we have mentioned the graph, which I've got a picture of up in the top right corner, and we're going to be discussing how we achieve threshold. So if the stimulus is big enough, then we will have enough energy to stimulate an action potential. So how this happens is because there's enough energy in the environment to open those voltage-gated ion channels, and therefore enough sodium enters the axon, allowing the internal environment to get from negative 70, that's our resting membrane potential, and climb all the way up to plus 40 millivolts. Again, this number may vary. Sometimes you see sources quoting as plus 35. Either would be acceptable in your answers in an exam. Now, once you get over the threshold potential, which is negative 55 millivolts, you are then committed to an action potential occurring. This is known as an all or nothing event, and an action potential is going to occur if this energy level is reached. All right, so depolarization. Sodium ions start to enter the membrane as a result of sodium voltage-gated channels opening. More voltage-gated channels start to open, so that's a kind of positive feedback response. This will rapidly change the charge on the inside of the cell. As we get more and more sodium entering, all voltage-gated ion channels will start to open. This will result in the inside of the membrane becoming more positive than outside, so we have reached peak of depolarization, or plus 40 millivolts. What is important to notice is that the potassium voltage-gated channels still remain shut, so sodium is inside the membrane, but so are the potassium ions. Okay, so what we are seeing on the up phase of the graph, depolarization, is the voltage-gated channels opening for sodium only. Sodium rushes into the cell and we reach the peak of depolarization, where we now have a much more positive intracellular environment than was previously there. Now that we've reached the peak of our depolarization, we now have to repolarize. So an increase in sodium ion levels become resistant to any more sodium entering the cell, and this normally happens around that plus 35 to plus 40 millivolt level. This is where we get a switch. So potassium voltage-gated ion channels will start to open, and instead of sodium rushing into the cell, potassium will start to rush out of the cell by diffusion. What happens here is it means that we start to get a swap in ions, but this will lead to a reversal in polarity. So we now have an interior of our axon fiber that is negative once again. So what the membrane is trying to do is return to its resting potential. Again, another little cartoon showing you how this happens. So the potassium channel is open, so we've reached plus 40 millivolts. Sodium is inside the cell. Potassium is starting to move out of the cell by these voltage-gated channels opening up. So repolarization, the sodium-potassium pump is still working to try and correct this ionic imbalance. So that is to say that the sodium-potassium pump is trying to get the membrane back to negative 70 millivolts. What we are talking about here is this correction mechanism. So the sodium-potassium pump is trying to do its best to repolarize. This all seems quite like a huge event that's taking place, but actually you've got to remember this is happening on a microscopic level, so it's not all the sodium and all the potassium in your body switching places at the one time. All right, so we're back to our graph again. Just to recap, resting membrane potential is this flat line here at negative 70 millivolts. if there is a big enough stimulus to cause an energy change in the environment, we will have depolarization, which is where sodium channels open and sodium will rush into the cell. This results in depolarization, and at peak depolarization, we start to repolarize. So repolarization, the sodium ion channels start to close, so no more sodium can diffuse, but the potassium ion channels open. So when the potassium ion channels open, potassium ions will diffuse out of the cell membrane into the extracellular environment. And the point of this is to try and get back to this negative internal environment. So you can see if you go back here to this graph, it's successful in repolarizing the internal and external environment. However, it does too good a job here, and we end up with something called hyperpolarization, which results in a refractory period. So hyperpolarization is where it is impossible to stimulate the nerve to conduct another action potential. What actually happens that causes this hyperpolarization is potassium channels are slow to close. So a little bit more potassium diffuses out than we need to, and that creates this really negative internal environment. So instead of getting to negative 70, we have a bit of an overshoot and we get down to something like negative 90 millivolts. While the action of the nerve is being adjusted, this is called the refractory period, and this allows the cell to recover so that an action potential can only happen in one direction. So we don't get action potentials going back towards the cell body. And then after we've had this refractory period where no action potentials can take place, the membrane starts to get back to normal, starts to get back to negative 70. How it does that is by the ion channels resetting, so they all remain closed, and the sodium-potassium pump is ticking over in the background, transporting 3 sodium and 2 potassium, maintaining this negative 70 millivolts internally. So just again to recap, the refractory period is where the potassium channels are a bit slow in closing, and this creates a slight overshoot in the potential difference. So during this phase, no other action potentials can take place while this refractory period is going on, and we are adjusting the membrane potential to get back up to negative 70. Okay, so let's look at this graph again with respect to sodium potassium. Here at the stimulus point, sodium channels will start to open. At depolarization, we start to get lots of sodium ion channels opening. Therefore, we have this very fast upshoot of depolarization. And at the peak of depolarization, we know that all the sodium channels are have been opened and they will start to close. On the other side of the action potential graph at repolarization, we have the potassium channels starting to open, and down here in the refractory period, they are starting to close. However, that does take a little bit of time, which is why we have this overshoot of negative internal environment. We start to get back up to normal because of the sodium-potassium pump. Okay, so this cartoon here goes through everything that we talked about. So you have closure of the sodium channels and the potassium channels. These voltage membranes, gated channels remain closed while the sodium-potassium pump is working in the background. That is at -70, so we are at the resting membrane potential. If there is a stimulus in the environment, you can see where the red and the blue meet at this line here, we start to get some sodium channels opening, but not all of them. As the sodium starts to enter the cell and we do have enough energy to open up all those channels, you start to get a rush or an influx of sodium into the cell at number 3, and you can see here that all the sodium channels are open, but the potassium channel is shut. At the peak of our action potential, we know that the sodium channels start to close and the potassium channels open, and you can see that in this diagram here. Number 5, this is our refractory period caused by hyperpolarization, and this is where we have some potassium channels still not closing in time, and then eventually we reset and get back to our resting membrane potential where the sodium-potassium pump starts to reorganize the sodium and potassium ions to make sure that we have the right level on each side. Okay, so here's a couple of exam questions just to test your knowledge about what we've looked at. Key with exam questions is never just go straight to the question itself. If you are given a diagram, please make sure you read it. It's there for a reason. In this question, you might look at this and think very quickly, that's obviously a sensory neuron. So therefore, this side must be the presynaptic neuron side. But if you look at the direction of the impulse, this gives you a clue as to which side is the dendritic side and which side is the axons. So you should have noticed that the direction of impulse moves from dendrite to axon fiber. So A would be an axon terminal and B is the cell body. Okay, with this question, we are testing your knowledge of what we've been talking about with respect to action potentials. I would like you to pause the video and have a go at describing what is taking place at X and Y. Okay, so hopefully you were able to clearly recognize that X is depolarization and give a description of what's going on. Even though you may have memorize the numbers plus 35 or plus 40 millivolts, it's important that you look at the question and look at the numbers that they are giving you. If you're given a graph with data like this, you should always quote the data from the graph. Hopefully you noticed that the Y is referring to repolarization, and again we are quoting numbers from the graph. Alright, so a task to finish off this lesson, sketch your own action potential graph and draw what is happening at each stage on the line and explain what's happening.